So Adam, you'd asked me at the end of last class, you'd asked me about when, I don't think you phrased it quite this way, but you'd asked when is the in-center on the Euler line, right? Well, you asked sort of why it isn't, or can we prove it isn't, or something along those lines. I was curious about your question. I looked it up, and I told you this. I'd said sort of if you choose an arbitrary triangle, right? Choose an arbitrary triangle, the chance of the in-center lies on the Euler line is 0%. Almost certainly it will not be, which has a mathematical meaning, but it is true. If you choose an arbitrary triangle, the in-center is not going to lie on the Euler line 100% of the time. Doesn't mean it always doesn't, it just means probability, 100% it's not going to. I looked it up. The actual answer is the in-center is on the Euler line if and only if the triangle is isosceles. So, to answer your question then, of can we show it's not, if we know that, which we're not going to prove, it's hard to prove that. I don't see any way to do it without using more advanced results. But to show that it's not, all we need is a counterexample, right? And if we believe that that's true, that it's on the Euler line if and only if the triangle is isosceles, then to find a counterexample, just choose something that's not isosceles, right? And though if you still just choose an arbitrary non-isosceles or scalene triangle, you're going to have to compute some stuff. It's going to be where's the Euler line, where's the in-center. Here's a very easy counterexample. Take a non-isosceles right triangle, right? So something like that. What's the Euler line for this thing? So this is a right angle. Well, where's the circumcenter? Where's O?
It's on the hypotenuse.
It's on the hypotenuse, and since this is the diameter of the circumcircle, it would be right there in the middle, right? So maybe right around there. There's O. Now it's not too hard to think about where's G or where's H. H is even easier. The orthocenter, since these are right angles, the feet of the altitudes is right there. Right, there's H. So there is the Euler line. But where's the in-center I? In-center I has to lie on the angle bisector from this right angle, right? And the angle bisector, this would be 45 degrees. This is obviously less than 45 degrees, something like that. So I is somewhere along that line, which is not on the Euler line. So there's a very easy counterexample of the in-center not lying on the Euler line.
Doesn't that the line or the Euler line having a non-45 degree angle on both sides, wouldn't that have to mean that both the other angles are not equal in the original triangle?
Yeah, and that again, that would mean non-isosceles.
Oh yeah.
Yeah. By the way, here's a very long-winded way we could find I at this point. Of course, we know how to find it. Just take the bisector of one angle bisector with the other, or the intersection of one angle bisector with the other. But using Euler's formula from last time, we know the distance. We know the distance from O to I, right? You can compute that. Take the set of all points that are equidistant from O. So, or not equidistant. Take the set of all points that are a distance d from O. That would give you a circle around O. Right, all the points that are that distance d, then look for the point where it intersects that bisector. That would have to be I, right? It would be the point on this bisector that is the distance of d from O. Very long-winded way. I don't know why you would ever do that, but yeah. So anyway, that was an interesting question. Again, proving that it's actually on the Euler line if and only if it's isosceles, it's a hard result, but we'll move on. We finished that section last time. Next up, we've got 2F on Excircles. I'm slightly renaming his section. He calls these X-scribe circles. I'll tell you sort of why I'm renaming it in a second. But these are similar to incircles in the following sense. So, an incircle maybe I should say the incircle, is internally tangent. Underline the word internally, because that's something we'll change in just a second. Internally tangent to all three sides of a triangle. To all three sides. I'm going to draw this fairly small down here because I'm going to need a lot of space. But here's my triangle, A, B, C, and the incircle is tangent to all three sides. So what I want to do is look for other circles that are tangent to all three sides. Problem is, I can't do this internally, right? We've proven that the incircle is the unique circle. It's the unique circle that's inscribed in this triangle. So how else can I build something that's tangent to all three sides? Well, I can't in this picture. But what I can do is I can think about extending the sides. And so if I extend the sides of the triangle, now I can think about circles that are tangent to this side, and this side. If I allow myself to extend them, I can fit a circle in here. Let's see, the center, somewhere around there. I can fit a circle in here that's going to be tangent to all three of those sides. The drawing's going to be horrible, by the way, but not the worst. All right, so that's an example of an excircle. So if we extend the sides of the triangle, we can find three circles. Right, that's not the only one. We can find three circles that are externally tangent. Externally tangent to all three sides. Although you might take offense to me claiming that it's externally tangent to all three sides. As I write it, I kind of take offense to that too. It's obviously externally tangent to AC, but I don't know what this really means. Is it externally tangent to BC or not, even the extended version? But externally tangent to at least one side and then the other two extended sides. Okay, so I have two more in this picture. If I extend AC out and BC out in this direction, there's another excircle that overlaps this line a little bit the way I drew it, but not meant to. And let me extend this guy. It's pretty big. Okay, so these three circles, are called, and this is the word the textbook uses, Excircles circles. Or excircles of the triangle. So here's my problem with this. Everyone calls these excircles. They're all excircles, just like incircles are incircles. And incircles are inscribed in the triangle. right? So I guess it's natural to say excircles would be excscribed in the triangle. The problem is, and this is the word he uses, excscribed, the problem is no one else in existence spells this as excscribed, it's escribed. So I guess it would be natural to say excscribed. Even the pronunciation, escribe, excscribe, not a whole lot different. But if you look this up anywhere, it will not be spelled with an X. It's just escribed. And he calls the section escribed circles. Excscribed, my bad. So anyway, little bit of notation. The X circle that's opposite angle A, we're going to call it center I sub A. The X circle opposite angle B, we'll call it center I sub B. And the X circle opposite angle C, its center will be I sub C. Alright, so we denote their centers i.e. the so-called X centers, of the triangle. By IA, IB, and I sub C. In a particular order, the subscript tells you which circle it is, it's opposite a particular angle, but I won't write all that down, so we'll just say as shown. And we've got in radii of the triangle, now we have x radii of the triangle. The problem is we've got 3 different x radii, but that's okay, we can talk about all 3 of them. So the radii of these ascribed circles, the radii, I want to phrase this. The radii are r sub A, r sub B, r sub C, which are called the x radii of the triangle. So what's the first thing we really should do? The first thing we really should do is prove that these actually exist, right? That's what we did with the in-circle. We proved that there was indeed a unique inscribed circle in every triangle. So the in-circle always exists and it's unique. That's really what we should do here. We should prove that these always exist and are unique, but we're not going to. It's obvious though, right? You should be very, very easily convinced that I can fit a unique circle in here that's tangent to all 3 sides, right? How would you do this? Well, kind of the same way we intuitively describe the existence of the in-circle. Just put a circle down on here that's tangent to this side, and then expand it, right? Expand it until it touches here, and then if you need to move this point of tangency, that's fine, but keep blowing it up until it touches here. Right, so pretty clearly they exist, and there's exactly one of them. Not really that difficult to prove the existence of these things though, using similar techniques to what we did with the in-circle. You might have noticed when I was trying to draw these, I was sort of trying to figure out where the centers would be. It turns out, where's the center of the in-circle? It's the point of concurrence between the 3 angle bisectors, right? The center of this in-circle is the point of concurrence between the opposite angled bisector and these are the internal angles. This is the internal angle A. There's the external angle. Turns out the bisectors of the 2 external angles pass through as well. So you can prove that easily, and once you've proven that, it's not too hard to show that the circle actually exists. So existence and uniqueness, we won't prove it. Existence and uniqueness, we won't prove it, we'll just accept that clearly these exist. That alone is sort of an astounding result, by the way. I mean, it's really surprising in geometry and all the stuff we do with triangles that when you draw three lines based on however you're trying to draw them, it's not particularly uncommon for the three lines to be concurrent, right? But anytime three lines are concurrent, it's sort of a bit of a miracle. There's no reason to think they would have to always intersected at this one point. Got a few other things though that are interesting. Do I want to talk about them? Hey, here's one interesting thing. The 9-point circle. I'd mentioned that this guy, Fehrbach, had originally proven the existence of the 9-point circle. Doesn't really get it named after him too often though, because he really proved the 6-point circle, right? He proved that there's a circle passing through the feet of the medians and the feet of the altitudes, right? He didn't do the Euler points. So 9-point circle was technically established, I think about 30 years later by someone else. But he did prove a rather famous result that is known after him, that the 9-point circle, or rather, let me phrase it a different way, that the in circle is internally tangent to the 9-point circle, right? So there's a point somewhere on the in circle, known as the Fehrbach point, that's internally tangent, it's tangent to the 9-point circle. Right, so there's exactly one point where it touches the 9-point circle. But he did more than that. He proved that the 9-point circle, or rather the 3 excircles, are externally tangent to the 9-point circle. So there's a point where the excircles just touch and are tangent to the 9-point circle as well. That's a big result. That's hard to prove, but he did all of that. So that's sort of his famous contribution to the 9-point circle, other than technically discovering it. So we won't go into any of that stuff. What are we going to do? We're just going to prove one theorem about the x radii. So for an arbitrary triangle, I don't have to give it a name here, there's no reason to name it, but we'll give it a name anyway, triangle ABC. There's this really interesting relationship between the in-center and, the in radii and the x radii. And it's the following. It's 1 over the in radius. Did I say in radii? There's only one of them, the in radius. 1 over r is equal to 1 over r sub a plus 1 over r sub b plus 1 over r sub c. Not obvious at all from this picture, right? It's really not obvious as to how they should be related. You'd think they would be, right? Because they're all based on the sides of the triangle. But there's the actual relationship. One thing it shows pretty obviously, I think, is that equation there establishes that the excircles are always bigger, right? The smallest it can be is 1 over r. So the excircles are always at least as big as the incircle. So in particular, the excircles are always bigger. Than the incircle. Which again is completely obvious if you think about how they're constructed. But that formula there establishes it as well. So we want to prove this. Before we prove it though, we're gonna go with a lemma, actually 2 lemmas I think. One isn't exactly stated in the book, but I want to spell it out very clearly. So, here's lemma 1. Which is something we've talked about. It follows immediately from stuff we've done, but I don't think we've ever exactly stated this or proven it. So I just wanted to separate it for a moment. Two tangents to a circle from an exterior point are equal in length. By the way, not exactly a technical result like I usually classify lemmas as. This is worth being called a theorem. If I'd stated it earlier, I would have just called it a corollary of the previous result. But we'll use it to prove that theorem. So we'll state it. We'll call it a lemma. Have we proven this in the past? I don't remember proving exactly this. So I won't write down a formal proof, but here's the idea. Just take a point P, and from P there's exactly two lines that are tangent to the circle. So here's one. That point is X, and here's the other, Y. So my claim is that PX and PY have the same length. Not hard to show at all. Take the center of the circle, so take the center, O, and build two triangles out of this. What's angle PXO? Yeah, doesn't look like in this picture, it looks a little less than 90, but if this is a tangent, then that must be right angle. That must be right angle. Both of these, OX and OY, they have the same length, they're just equal to the radius of the circle. And that's enough. The hypotenuse of the two triangles are the same length. Well, let me rephrase this. It's a right triangle, both of them are right triangles. Have the same hypotenuse, and two legs agree, so by hypotenuse leg, these are congruent triangles. So by hypotenuse leg, triangle POX is congruent to POY, and that means that PX and PY are the same by identifying corresponding sides. So perhaps for the first time ever, when I say I'm just really going to sketch a proof, that really is a sketch. I haven't written down the details at all, but here's the idea. Although I said I might have called this a corollary of a previous theorem, because this really is. Here's a separate proof. And this is a theorem that we've actually invoked very, very recently, except we did it with a point that was internal. Take an external point and just draw two lines to cut through the circle, right? Draw two secants. So there's X, Y. When I say recently, I think we did this, we moved it last class maybe. There's U and V. So what was our result? Our result was that this product, PX times PY, depends only on P, not the line you choose, right? So PX times PY is PU times PV. PX times PY is PU times PV. How do you get the tangent case? Well, it's a limited case of this, right? The tangent case pushes X and Y closer and closer and closer together, right? So just take secants where X and Y get closer and closer together. So in the limiting case, in the tangent case, where X and Y are at the same point, that's the tangent case, right? So in the limit, we get the tangent case where x and y are the same point, so this would just give me px squared is pu squared. Just purely mathematically, this doesn't mean px is equal to pu, it means px is plus or minus pu, but because line lengths can't be negative, it does mean px is equal to pu. So kind of follows as an immediate corollary of that previous big theorem we had. Any questions? All right, so there's lemma 1. I just wanted to sort of isolate that out because we'll use that many times in the next lemma. Lemma 2 is actually fairly technical. And we'll only use it to prove the next theorem, or the theorem we stated already. Lemma 2. The length of the tangent from a vertex of a triangle to the opposite excircle is equal to the semiperimeter, S. The length of the tangent from a vertex of a triangle to the opposite excircle. So what's this saying? Yeah, I think it would help to parse this with a picture. Let's see, so here's my triangle, I'll call it, let's fit a small triangle here. A, B, C. So we're going to look at the excircle that's opposite angle B, so we'll fit an excircle in here somewhere. Not terrible. There's this excircle, and let's call these points of tangency. The point of tangency with this side, we'll call that P. This point of tangency, we'll call this Q. Right, so what this is claiming is that by lemma 1, right, by lemma 1 I've got these two tangents drawn from the point B is the way you can think of this. By lemma 1 I know BP is equal to BQ. This lemma says that BP is equal to BQ. Both of them are equal to S. So i.e. BP equals BQ, that's by lemma 1, and that's equal to S, is the claim. All right, so the proof, we're not going to sketch this, we'll write down all the details, so I should tell you exactly where P and Q are. Y, by the way, I'm going to call this point Y, the point of tangency of the excircle with A sub C, we'll call that point Y. And we'll just write down exactly what all these points are, so let Y be the point of tangency of the excircle with, let's say, which excircle am I talking about? I'm talking about the excircle that's opposite angle B. Point of tangency of the excircle opposite angle B or vertex B. So point of tangency of that excircle was side AC. And let P and Q be the points of tangency with the extended sides. With the extensions of AB and AC respectively. Extensions of AB and AC respectively. And since we have a nice picture of exactly what's happening, we'll say as shown. So by lemma 1, we already know BQ equals BP equals BQ. So by lemma 1, we know BP equals BQ. Right, there are two tangents to a circle from an exterior point. What we want to show is that this equals S. I want to show these equal S. How am I going to do that? Well, I'm actually going to invoke lemma 1 again, but with two other tangents from a different point. How about tangents from A? Well, AP is a tangent and AY is a tangent to the circle. So by lemma 1, AP must equal AY. So also by lemma 1, we have AP equals AY. So let's call this equation 1. What's BP? Right, I'm hoping to show that BP or BQ equals S. So let's work with BP. Well, another way to write the length BP is as BA, let's call it AB, AB plus AP. There's AB plus AP. But by our above observation, AP is equal to AY. So I'll call this AB plus AY. Completely similarly, you do the same thing with side BQ. So similarly, let's get equation 2. BQ would be BC plus CQ. But hold on, CQ is equal to CY. So this is BC plus CY. Now, all we have to do is add them together. So adding 1 and 2 gives BP plus BQ. On the right, so add both the right-hand sides, I've got AB plus AP plus BC plus, oops, sorry, I'm copying here. I don't want AB plus AP, I want AB plus AY. AB plus AY plus BC plus CY. So separating out a few different pieces, AB plus BC plus AY and CY. But what does AY plus CY equal? That's just this whole side, right? That's AC. AB plus BC is AC. What's that equal? Well, that's the length of the perimeter of the triangle, right? So that's 2 times S. What have we shown? We've shown BP plus BQ equals 2S, but hold on, we already know BP and BQ are the same, so I can just think of that as 2 as BP. And that tells me, dividing both sides by 2, that tells me BP is equal to S. And we're done. So not a difficult proof, just uses sort of over and over again the fact that tangents to a circle from the same point always have the same length. In fact, there's only 2 tangents, so it just means both tangents are the same length. Any questions about this proof? All right, so finally now, we can prove the main theorem. We didn't give the theorem a name, but if we just say main theorem, well, there's only one theorem in the section, so it's pretty clear what we're referring to. And let's see, I'm gonna put up a picture again before we start talking about things. So let's essentially draw the picture we just had. There's A, B, C. But there's our circle. There's point P, and I don't think I need Q at all in this picture, or Y. So that's all I'm going to draw. All right. So my first thing I want to claim is what I've already told you. Is that the center there, the X center of this triangle, the X center that's opposite angle B, or the center of this X circle, is actually on this angle bisector from B. So how are we going to do that? Well, let's note that IB, I don't think the textbook proves this actually, so this is worth going through. Note that it's equidistant from P, and I lied. I do want to label this point Q. It's equidistant from P and Q. And both of them, they lie on the extensions of AB and AC, or sorry, AB and BC, right? Which lie on the extensions of AB and BC, respectively. And that's enough. That's enough to establish our claim now. Remember, in proving, I believe it was the existence of the incenter, we had to prove a lemma before, which said that a point is on the angle bisector if and only if it's equidistant. Both of those are right angles, so those are the distances to those lines. If and only if it's equidistant from both of the sides that make up the angle. All right, so this showing that I sub B is on the bisector of angle B. Maybe that's why the textbook doesn't formally prove it, is because it's kind of obvious. By the way, I labeled the wrong right angle there. That's the right angle. Do you guys remember that? A point is on the angle bisector if and only if it's equidistant from both sides. Okay, so I know that the center of this excircle must lie on that angle bisector. And by the way, as I told you before, if you really want to know exactly where it is, it's also concurrent with the two exterior angle bisectors. That's technically how you find them. But we won't prove that. So now, let's look at triangle BPIB. Let me just erase that because it's going to be confusing. Okay, so that's a right triangle, right? This is a right triangle. With one leg, BP, as we just showed by our lemma, BP is equal to S, right? So there's one leg. BP equals S. And the other leg, P I sub B, what's the length of that? Well, that's just the radius of this triangle, right? It's the x radii of sort of opposite angle B. So this would be the radius of that excircle, little r sub B. So looking at just this angle, doing a little bit of triangle trig, tangent of this angle, which is b over 2 because it's an angle bisector, tangent of b over 2 would be opposite over adjacent, right? So it should be r sub b over s. But that's using SOHCAHTOA to figure this out, right? Another way I could express tan b over 2 is using the law of tangents. So also, by the law of tangents, tan of b over 2, which as we just saw is r sub b over s, invoking the law of tangents, this would be the square root of s minus a times s minus c over s minus b. Okay, so this means that r sub b is going to be, I need an extra s in here, s times s minus b. Sorry about that. So multiply both sides by s, bring the s inside the square root as an x squared, and one of those cancels with one on the bottom. We end up with s times s minus a times s minus c over s minus b. Here you're essentially done. All I have to do now is do the algebra. So there's r sub little b. What's the form of this? The b means I'm missing the s minus b up top, and the s minus b ends up down the denominator. So similarly for the other radii, rb, rc. Sorry, ra, rc. So r sub a would have s minus a in the denominator, right? R sub c would have s minus c in the denominator. And already we've done actually a little bit more. We've done a little bit more than the theorem stated. The theorem just stated there's a nice relationship between the x radii and the n radii, n radius. Here we've actually found exactly what they are. Right, so this is a little bit more than is actually stated in the theorem. Maybe you want to make a note of that. But now we just have to do the algebra. We've got 4 minutes. Let's see how quickly we can do it. So now, 1 over r sub a plus 1 over r sub b plus 1 over r sub c, what's that going to equal? It's reciprocal of the expressions we just had, so we're going to have s minus a over s times s minus b times s minus c plus s minus b over s times s minus a s minus c plus the square root of s minus c over s times s minus a s minus b. What do I want to do? I want to put them over the same denominator, common denominator, so that I can combine them together as a single expression. How am I going to do that? Well, the first one I'd have to multiply top and bottom by s minus a. Second one I'd multiply top and bottom by s minus b. Third one I'd multiply top and bottom by s minus c. So if I do that, I've got s minus a squared. Inside of a square root, this becomes s minus a over the square root of s times s minus a, s minus b, s minus c. Plus s minus b squared inside of a square root is just s minus b times s, square root of s minus a, s minus b, s minus c, plus s minus c over the square root of s minus a, s minus b, s minus c. Sorry about the handwriting. They're all over the same denominator, so I can combine them now. What do I have up top? S plus s is 3s minus a plus b plus c. What's a plus b plus c? That's the perimeter. So that is 2s. What about the bottom here? Square root of s times s minus a, s minus b, s minus c. That should look familiar to you. What's that equal to? That's Heron's formula, right? So that's k over k. 3s minus 2s is just s over k. And we proved at one point, this goes back, we've shown before that k is equal to r times s. So this is s over rs, which is 1 over r, and we're done. When did we prove this? I believe back in the computation section. I think when we were proving Heron's formula, somewhere in that proof, I believe we had that formula. It pops up in some proof somewhere, so we'll just invoke it now. And we're done with about a minute to spare. So, any questions? All right, have a nice weekend, guys. I'll post up homework either this evening or tomorrow sometime. I think the textbook is fairly limited on stuff for Excircles, but maybe they have a good problem, and then we'll do some Excircles stuff. See ya.